Hi everyone, I'm Ling. I'm a software engineer, hobbyist game developer, and recent graduate from the University of Chicago. Welcome to this course on solving backtracking problems. Whether you're new to coding interviews or already have experience with backtracking problems, this is the crash course for you. We will learn about an all-purpose template that helps you solve any kind of backtracking problems, and we will apply the template to LeetCode problems like the 8 queens problem or the Sudoku solver problem. This is exactly the template that I use for my code interview problems when I'm developing algorithms for my games or even once in my research on a non-convex optimization problem. I hope you're excited, and let's dive right into this versatile template. You can find this template in my GitHub gist linked to in the video description below. Let's start with some keywords and concepts in backtracking problems that will help us understand the template better. The first keyword, state. Essentially, a backtracking problem is asking you to find valid states. Take the n queens example that we will solve later in this video. An example of a state is just arbitrarily placing n queens on an n by n board. For example, here we are placing 4 queens on a 4x4 board. On the contrary, an example of a valid state requires that the queens are placed in a fashion that they cannot attack each other. If you aren't familiar with the rules of chess, don't worry. The moves of queens are pretty straightforward. A queen can move horizontally, vertically, or diagonally. Therefore, for our placement of the n queens to be valid, they can't stand on the same row, the same column, or the 2 diagonals. So how do we construct a valid state like this? Well, we build up from previous states. Suppose we're starting from the blank n by n board where no queen is present. We can put our first queen arbitrarily wherever we want. Let's say we put it here. Then where can we place the second queen? You can see now our choices are limited, or in background terminology, our candidate states are limited. Because we place the first queen here, this entire column, this entire row, and the 2 diagonals are now unavailable for new queens. Let's say we just put the second queen here, where it's available. Next, we try to see where we can fit in the third queen. Our candidates are now more limited because we put the second queen here. This column, this row, and this diagonal is not available. So our third queen can only go here. Finally, let's place the fourth queen. Because this third queen is here, it blocks this diagonal, and this row and this column, leaving our fourth queen to stand here. Great! Now, is this global layout a valid solution such that no queen can attack each other? Well, we've already seen in our checks. So like this, we have found a valid solution to this n-queen problem. As a counter example, consider if we place the first 2 queens like this. Now, all these cells marked in red are unavailable, and we only have 1 left for the third queen, and nowhere to place the fourth queen. This means that this succession of state searches fails to lead to a valid solution. And this is pretty much it about states, identifying candidates to build the next state and validating a final solution. Now let's look at how these procedures are defined in our template. There are 4 functions in our template. The first 3 is valid state, get candidates, search are helper functions. The last and most important one, solve, is the entry point to our program. The solve function is indeed the one that a LeetCode problem is asking you to write. It is responsible for returning the valid solutions. Let's look at the helper functions one by one. Is valid state. This function takes in a state and returns a boolean. It validates whether a state can be used as a final solution. In our queens problem, a state is a valid solution if all n queens are placed on the board and none of them can attack each other. Get candidates. This function finds a list of candidates that can be used to construct the next state. Search. This is a recursive function. It calls the previous two helper functions and checks if the state is a valid solution to our backtracking problem. If it is, it records the solution by making a deep copy of the state. Note that we do need a deep copy instead of a shallow copy because we will continue to modify the state as our search goes. But we need a static snapshot of the valid state here. This line of return is commented out because depending on the nature of the problem, we might need to find all valid solutions or just one. If we only need one, we can return as soon as we have found it. Otherwise, we continue on until we exhaust all the possible search states. Continue down here. If the state isn't yet a valid solution, we find candidates to build the next state. Recall that getCandidates return a list of candidates. For each one, we add the candidate to the state. In the queen's problem, for instance, suppose our state only contains the position of the first queen. Here we add a candidate position for the second queen. Then we take this modified state and recurse on it by calling the search method on this modified state. If the modified state is valid, the solution is recorded, like here. Otherwise, the search function fetches candidates for this modified state and recurs further. Eventually, for some state, there is no more possible candidate. Think that example where we cannot place a fourth queen anywhere because all the spaces have been occupied. After returning from the recursive search, we restore the modified state to the original by removing the candidate from the state. Again, in the queen's example, we undo the placement of the second queen, and now we only have the first queen. As for solve, it starts with an empty list of solution and an empty state. It calls search on the state and this list of empty solution. Search will eventually fill up this list of empty solutions and then return the list of solutions. And remember, this is the function that LeetCode problem is asking us to write. When using this template, keep in mind that this is only a template. So your helper functions is valid state, get candidates. They might take in additional parameters. Search might also return a Boolean indicating whether a solution has been found and return early if there is one and only one valid global solution, like in the Sudoku problem that we will eventually see. This concludes our brief introduction to the template. Next, let's solve the queen's problem hands-on in LeetCode. Here we are on LeetCode number 51, the n-queens problem, which is a LeetCode hard problem. Let's first read the problem statement. Given an integer n, we want to return all the distinct solutions to the n-queens puzzle, and we may return the answer in any order. And LeetCode has a specific format for us to represent the board. For our 4 queens example, these are the 2 valid solutions. And here, we denote that the first square on the first row is not occupied, the second square is occupied by a queen, the third one is not occupied, the fourth one is not occupied. And on the second row, the first 3 squares aren't occupied, and the last one is occupied by a queen, so on and so forth. And in the case where n is 1, the queen can only be on the single grid, so that's the solution. Before jumping into the code, let's first think about how we may represent this problem logically. We might be tempted to represent this board data structure as a 2D array, but it's actually a little bit waste of space to do so. Since no queens can be on the same row or the same column, we may just keep a 1D list that tracks the queen's position in each row. Concretely, for this example here on the left, for the first row, the queen is in the second cell. So the first index is 1. For the second row, the index is 3 since the queen is in the 4th cell. And this here is 0. This here is 2. Following the same logic, for the example on the right, the first index is 2, the second index is 0, the third one is 3, and the last one, 1, because the third cell, the first cell, the fourth cell, and the second cell. So this is the way that we will represent each state as a 1D list for this backtracking problem. Now I'm going to grab my template and put it into LeetCode. I'm going to move the solve method on top. As already mentioned, the solve method is basically the one that LeetCode is asking us to write. So for the solve and queens problem, we will just be adapting the solve function. So solutions is initially an empty list because we may return all the valid solutions in any order. Then my starting state is just an empty list because we haven't placed any of the queens into the board just yet. Then we call self.search on the state, giving it our list of solutions to append to, and the parameter n for the n queens. After the search is complete, we return the solutions. Let's go ahead and remove this part. Great. Now we will write the isValidState function. It will take as parameter self, state, and n. For state to be valid, it needs to put all n queens onto the board. So if the length of the state is n, then we know we have already put all n queens onto the board. As for the condition where no queens can attack each other, we will handle it in the getCandidate function. Essentially, we will only return candidates that land on valid squares that won't be attacked by the previously placed queens. So self state n. Great. So here we are constructing candidates based on the state that we are given. If there is no state, meaning that we are starting from a blank board, we may place the first queen anywhere we want. So if not state, we return all the possible indices. If the state is not empty, we find the next position in the state to populate. So position is the length of the state. If we have already placed the first queen, we want to place the second queen. So candidates initially start from all the indices, and then we prune down candidates that aren't valid. I'm using a set because it's better than walking through a list. And set guarantees uniqueness. All right, let's prune down candidates that place the queen into a text. So for row column in enumerate state, we discard the column index if it's occupied. So candidates dot discard recall that our state is recording the column index for each row. Now we discard the diagonals. So distance is the distance between the position and the row index. Because we're trying to put a queen in the second row, now that we have already filled in the first row, we want it in a place that cannot be attacked by the first queen diagonally. So this one is out of the question, and this is column plus distance. This one is also out of the question, column minus distance. And at the very end, we return candidates. Now let's define our recursive search function. It should take self, states, solutions, and n. We just adapt the template. So if self.isValidState, state, n, we just add it to the solutions and return. Otherwise, if we come down here, for candidates in self.getCandidates, state, n, we recurse. Because our state is a list and no longer a set, we do append candidate and then call self.search, state, solutions, and n. And then to restore the modified state back to our original, we pop the lost entry. Great. So this here is the only thing that we need to take care of because LeetCode wants us to output strings. And here we have is a list of column indices. So let's define some additional helper functions here. State to string, self state, n, and we expect the output to be just like here. So here's how we convert our list of indices to this output string specified by LeetCode. So the return is just a list. For I in state, because one means that the queen is in the second cell and the other cells are empty, we just append the strings for the empty cells as well as the string for the queens concatenate together to get the return value. String is this dot, meaning the empty square, times I plus the queen's position plus the remaining empty cells. And ret.append string, and we return the ret. And here instead of solution append state.copy, we do state string, and state string is produced by self.state to string state. Great. Let's now run the example code to see how we did. Alright, cool. Looks like our output is accepted. Let's submit and see whether we can pass all the test cases. Great. You can see that our runtime is better than almost 70% of the submissions, and also some memory usage is better than 7% of the other submissions. We are definitely using some memory because of the recursion, but that's totally okay for backtracking problems. Next, we'll solve another LeetCode hard problem called the Sudoku solver problem. We're now on LeetCode problem 37, the Sudoku solver problem, which is a hard problem. If you don't already know what a Sudoku puzzle is, you can read the description. So a Sudoku solution must satisfy all the following rules. Each of the digits 1 to 9 must occur exactly once in each row and in each column. Also in 9 of the 3x3 sub-boxes of the grid. And LeetCode used the dot character to indicate empty cells. So for example here, LeetCode wants us to write a program that fills out this Sudoku puzzle in a valid way. The board is represented as a 2D array of strings. Some might be numbers, some are empty cells, and LeetCode wants us to solve the problem and modify the board in place. The constraints are that because it's a Sudoku problem, the shape is 9 by 9, and each cell is either a digit string or the empty string. And it's guaranteed that the input board has only one solution, so we may return early if we found only one solution. Let me copy-paste my template and jump into the problem. Alright, so again we adopt the solve function like this. Because it asks us not to return anything and just modify the board in place, I think we'll just need to do self.search board. And then we can get rid of this solve function. I'm going to have to define some constants here. So the shape is 9 by 9. The grid length is 3 by 3 if we are trying to validate the sub-boxes. And empty is represented as this dot here. And all the digit strings are like follows. So string number for number in range 1, shape plus 1. So this gives us the string from 1 to 9. And I'm going to wrap it in a set because the order is not important. And I know I'm going to need this when I'm traversing the grid. Great. So let's start by writing the isValidState function. So it should take self and the board and check if the board is a valid solution. So let's validate all the rows first. For row I'm going to just define some helper function later down. So let's do first self get rows, which returns each row of the board one by one. If my row is equivalent to all the digits, then it's a valid row. Otherwise, it's an invalid row and the entire board is not valid. If not, set row is equal to self.digits, return false. Validate. Similarly, we validate the columns. Get cos. Return false. And lastly, we validate the subboxes for grid in self.getGrid board. And if all the rows are validated, all the columns are validated, and all the grids are validated without causing this false return early, we return true, meaning that the board is now a valid solution. Now let's write get candidates. So self, board, a row, and a column. I'm using a row and a column because for a cell, I want to know which row and which column it is on to determine what digits have already been used and what are left for us to use as a next state. So used digits is a set of digits, and I'm going to remove digits used by the same row. So used digits dot update self dot get kth row. This is another helper function that I will define later down. Remove digits used by the same column. So used digits dot update self dot get kth column, board, and a column. And remove digits used by the 3x3 subbox. So used digits dot update self dot get grid at row and column. So we need to identify for an arbitrary cell which grid it is on. Board, row, col. And lastly, because we might have already used the empty string here when we are doing the updates, we subtract those from our used digits. Self.empty is the constant that we defined for the empty string. And candidates are just whatever that's left for us to use. So the unused ones. And that concludes our getCandidate function. Now we are moving on to do search. Because we only have one single solution, we don't need the list of solutions here. So self and board. We have isValidState, so if self.isValidState board, we return true, found solution. Otherwise, we find the next empty spot and take a guess. So for row, index row in enumerate board, for column index, the actual element in enumerate row. If the element is the empty string, so self.empty. If this is empty, find candidates to construct the next string, next state. candidate is self.get candidates board. Now that we have the row index and column index, we pass those in. We modify the board in place as the problem instructed us to do so. Candidate. Remember that candidate is just one of the digit string. And because here our search returns a Boolean, if one of the search actually finishes, that means that the board has been modified in place and our problem is solved. So is solved is now equal to self.search board. And just to add some comment here, we recurse on the modified board. If is solved, now we just return true, meaning that the entire search has completed. Otherwise, we undo the wrong guess and start anew. So we make this entry back into the empty string that it was. And down here, we have exhausted all the candidates. But none solves the problem. We return false because this is an invalid succession of searches. And if no empty spot in the first place, then we just return true. And we can get rid of this boilerplate code from our template. Now the structure is pretty much clear, and all I need to do is to fill in those helper functions. Helper functions for retrieving rows, columns, and grids. So here are my helper functions for retrieving rows, columns, and grids. This is pretty straightforward because our board is just a 2D array, and to retrieve the kth row, kth column, or grid at a certain row and column indices, we are basically just doing some really smart indices and sometimes relying on the power of itertools. I will post my complete code on my GitHub linked to in the description, so you can digest those helper functions on your own. Now let's run the code and see what we get. Great, our output is accepted. Let's submit and test it against all the test cases. Awesome! With this template, we solved 2 LeetCode hard problems. To recap, a backtracking problem is all about finding valid states. To solve for a valid state, we identify candidates that satisfy the problem constraint and use them to build upon our current state. Once a modified state is valid, we add it as a final solution. Now that we have solved 2 problems hands-on, let's take another look at our template. Recall that we have these 4 functions. IsValidState is a helper function with a Boolean return value that validates whether a given state is a final solution. GetCandidates is another helper function returning a list of candidates satisfying the problem constraint based on our current state. Search is a recursive function that calls the 2 helper functions, IsValidState and GetCandidates, and recurs on itself. Lastly, solve is the function that a LeetCode problem is asking you to write. It does nothing fancy other than initializing an empty list of solutions, an empty state, and calling search on them. For more practice problems on backtracking, go to LeetCode.com and in tags, search for backtracking. This filters out a list of questions that all shares the backtracking idea. You see we already solved Sudoku solver and queens. If you're looking for a medium hard problem, I recommend the subsets problem. This is about finding all possible subsets or power sets of a given integer array. It is pretty easy to identify a backtracking problem when we are asked to find all possible solutions and may return the solution in any order. As you can see in my submission details, I solved the subsets problem using the exact template. As you go through more and more LeetCode problems and test how much you understand about the template, you will be better prepared to identify a backtracking problem once you encounter one in your coding interviews. This concludes our video and the only crash course you ever need for solving backtracking problems on your coding interviews. For more content like this, please subscribe to my YouTube channel, Lin's DevLab. I also post fun project tutorials and my game development demos on my channel. My latest tutorial is about building a Discord AI chatbot with the personality of your favorite character using entirely cloud-based technologies, and I'm sure you will enjoy it. Thanks for watching and best of luck preparing for coding interviews.